Jai to all. Today is my second lecture of fluid mechanics. In the previous lecture, we have discussed the basic definitions and terms related to the fluid mechanics and various properties of the fluid mechanics. And further, we have solved the general equations, general problems related to the properties. Now, in this lecture, I will discuss surface tension and capillarity, further capillarity behavior, expression for capillary and rise and fall, fluid pressure at a point, Pascal's law, and last slide will be references. So let us start now. What is surface tension and capillarity behavior? So surface tension is defined as the tensile force acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids such that the contact surface behave like a membrane under tension. So the surface tension is basically a type of tensile force. Okay, surface force is basically it is a tensile force which is acting on the liquid surface in contact with a gas or on the surface between two immiscible liquids. So immiscible means which cannot be mixed with each other. That type of liquids are known as the immiscible liquids. Okay, and during the behavior of surface tension, the surface will act like a membrane in tension. Okay, the magnitude of this force, that is the magnitude of tensile force, can be measured using force per unit length of the free surface. Okay, and it has the same value as the surface energy per unit area. Okay, so the magnitude of the magnitude of surface tension is measured as the ratio of force per unit length of the free surface, and its value will be the same value as the surface energy per unit area. Okay, so you can see in this figure that is this is the free surface of liquid where tensile forces are acting in this direction, in this direction, in this direction, in this direction, in this direction. Okay, now surface tension is created due to the unbalanced cohesive forces on the liquid molecules at the fluid surface. Sorry. So surface tension is developed or created due to the unbalanced cohesive forces acting on the liquid molecules at the fluid surface. Okay, it is denoted by the Greek letter sigma, and in SI units its unit will be Newton per meter. Okay, what is the unit of surface tension? Its unit will be Newton per meter. Now in this slide we have to develop for the calculation of surface tension on a liquid droplet. So let us discuss. Suppose in this figure this is a liquid droplet. Okay, and figure B shows the half part of this liquid droplet, and this direction of forces represent the surface tension. Okay, so let us assume a small spherical droplet of liquid of radius small r, its radius r, its radius is small r. Okay, here the symbols are mentioned here. Let sigma equal to the surface tension of the liquid. P is the pressure intensity inside the droplet in excess of the outside pressure intensity. So these terms are very important because we have to always remember that value of P is the pressure intensity inside the droplet, which is in excess of the outside pressure intensity. Okay, and D is the dia of the droplet. So let us cut this droplet into two parts. Okay, as shown in figure B. Now the forces acting on one half, that is the left portion, what are the various forces acting on this half part? Tensile force due to surface tension acting around the circumference of the cut portion. Okay, so this is the surface tensile force acting on the circumference area. Okay, now what will be the magnitude of this tensile forces? Its magnitude will be sigma, that is the surface tension, into length, because surface tension is calculated by the force acting per unit length. So what will be the value of length? The length will be circumference. Therefore the tensile force will be equal to sigma into pi d. Okay, now the second force, pressure force on the area, pi by 4 d square. The area of spherical droplet will be area of this portion, means this portion is showing as a circular portion. Therefore its area will be pi by 4 d square, and force will be P into surface area, means pressure intensity into pi by 4 d square, as shown in figure. As shown in figure C, P is the pressure intensity. Okay, capital P is the total force, where small p is the pressure intensity. So the total force acting on this surface will be capital P, which magnitude will be P, small p, into pi by 4 d square, and direction will be inward. And what is the direction of surface tension? It will be outward. Okay, now these two forces will be equal and opposite under equilibrium conditions. Means if the body is in rest condition, then the magnitude of forces, the resultant forces will be 0. Therefore, if we consider these two forces, that is the pressure force and surface tension, tensile forces, then it will be equal to P into pi by 4 d square equal to sigma into pi d. If we simplify it, then final intensity of pressure P will be equal to 4 sigma divided by d. So this is the final value of pressure intensity for a liquid droplet. Okay, small p is equal to 4 sigma divided by d, where d is the dia of the droplet. Using this equation, one can easily guess that if the dia of droplet is smaller, then pressure intensity will be greater. Okay, and this line also represent the same thing, that is the with the decrease of diameter of the droplet, pressure intensity inside the droplet increases. Okay, now next slide, surface tension on a hollow bubble. So what will be the value of surface tension on a hollow bubble? Suppose, as shown in figure, this is a liquid jet. Okay, this is the next topic. Now surface tension hollow bubble. Suppose there is a hollow bubble, okay, like a soap bubble. Hollow bubble is represented by the soap bubble, in which two surfaces are contact with air. For example, you can see here a hollow bubble like a soap bubble in air has two surfaces in contact with air, one inside and other outside. Okay, therefore there are two surfaces are subjected to surface tension. In that cases, what will be the magnitude for pressure intensity and surface tension? You can easily write it P into pressure intensity into surface area. This will be equal to the pressure forces, that is P into pi by 4 d square equal to tensile force acting on the bubble slope. This will be equal to 2 times of sigma into pi into d. Okay, so further if you simplify it, then it will give P is equal to 8 sigma divided by D. Means in case of soap bubble, the intensity of pressure can be given by 8 sigma by D, that is 2 times of liquid droplet. Is it clear? Okay. Now surface tension on liquid jet. So as shown in figure, this is a liquid jet, okay, having the diameter small d and length or height of the cylinder liquid jet is capital L. If we cut it into two parts, then the tensile forces will be acting in this direction, okay, that is the sigma will be acting outward direction, okay. Now we have to calculate the surface tension on a liquid jet. So let us consider P is the pressure intensity inside the liquid jet above the outside pressure. Sigma is the surface tension of the liquid jet, okay. Now calculate the forces acting on this and keep it equal to the all the forces, okay. Now force due to pressure forces will be P into area of semi-jet. Now area of semi-jet will be, this is the length and this is the width, okay. So area will be L into D and small p is the pressure intensity. So force due to pressure will be P into L into D, okay. Now force due to surface tension will be equal to sigma into 2L. 2L will be due to the total length at which surface tension will act equal to 2 times of L, okay. So force due to surface tension will be equal to sigma into 2L. Now if we equate these two forces, then we have to write P into L into D equal to sigma into 2L, okay. Now if you further simplify it, then P will be equal to sigma into 2 times of capital L divided by capital A into small d. Further L can be cancelled out, okay. Now let us move towards some basic problems related to the surface tension, okay. So in this question, the surface tension of water in contact with air at 20 degrees Celsius is given as 0.0725 Newton per meter. The pressure inside a droplet of water is to be 0.02 Newton per centimeter square, okay, greater than the outside pressure. Calculate the diameter of the droplet of water. So in this problem, the value of surface tension at 20 degrees Celsius is given, okay, and the pressure inside a droplet of water is also given, that is the 0.02 Newton per centimeter square, okay. Now we sorry. Now we have to calculate the diameter of droplet of water, okay. So the given data is already mentioned here. Sigma is equal to 0.0725 Newton per meter and pressure intensity is given in Celsius system. So first of all, let us convert into SI system, okay. So 0.02 Newton per centimeter square equal to 0.02 into 10 raised to power 4 Newton per meter square, okay. Let us consider the diameter of the droplet will be small d. If we use the equation for surface tension in liquid droplet, so what will be the equation? The equation will be P equal to 4 sigma divided by small d. So put all the values which are given here. P value, pressure intensity value is given here, 0.02 into 10 raised to power 4 equal to 4 sigma. Sigma value is already given here. So further, if you solve, then the value of B will be 1.45 mm. Now, what is the required answer? The diameter of the liquid droplet is 1.45 mm. Okay. So this problem is basically based on the formula basis. If you remember the formula, then you can easily calculate the required answer. Okay. Now second problem is the pressure outside the droplet of water diameter 0.04 mm is 10.32 Newton per centimeter square at atmospheric pressure is given. Okay. Now calculate the pressure within the droplet of surface tension is given as 0.0725 Newton meter of water. Now what are the required data to be calculated? Pressure within the droplet of surface droplet if the surface tension is given. Surface tension value is already given here 0.0725 Newton per meter of water. Okay. So finally we have to calculate the pressure within the droplet. Okay. So let us solve this. The dia of the droplet is given 0.04 mm. Then it will be 0.04 into 10 power minus 3 meter. Pressure outside the droplet is already given 10.32 Newton per centimeter square. Okay. If you convert it in a SI system, then it will be equal to 10.32 into 10 to the power 4 Newton per meter square. Okay. Surface tension is also given as sigma equal to 0.0725 Newton per meter. Okay. Now again we have to use the same formula as in the previous problem. P is equal to 4 sigma divided by D. Okay. Put all the values given here. So sigma value is already given 4 into 0.0725 divided by D. D is the 0.04 into 10 to the power minus 3. If you solve it, then the pressure intensity inside the droplet is given will be obtained as 0.725 Newton per centimeter square. Okay. So what is the pressure inside the droplet? It will be equal to the pressure intensity due to the surface tension plus pressure outside the droplet. Okay. So if you put the value of P, that is 0.725, and pressure outside value outside the droplet is already given here 10.32 Newton per centimeter square, and it will be converted into 10.32 into 10 to the power 4 Newton per meter square. Okay. So the final value of the pressure inside the droplet will be 11.045 Newton per centimeter square. Okay. So in this question there is a certain point to be remembered. Okay. The pressure value, that is a 10.32 Newton per centimeter square at atmospheric pressure. Okay. Outside the droplet is given. Okay. And further we have to calculate the pressure within the droplet. Okay. So whenever in the sessional or semester exam the question is asked, then you have to read it out, read it carefully, what are the required value to be calculated. Okay. And by saying example 1.25 and 1.27, it is clear, it clears the concept of the intensity of pressure how to be calculated. Okay. Now capillarity. So what is the capillarity? It is defined as a phenomena of rise or fall of a fluid surface in a small tube related to the adjacent general level of the liquid when the tube is held vertically in the liquid. For example, you can see in this figure a small vertical capillary tube is inserted in the liquid in a container having the liquid. Okay. If you insert this vertical capillary tube in this container which is already filled with liquid, then the liquid will move in upward direction. Okay. Gradually it will increase in the upward direction. Okay. Water level will be rises at certain time interval. Okay. And further after few time the surface will look like this. Okay. In concave way. Okay. So the phenomena of rise or fall of a liquid surface when a capillary tube is inserted in a container having a fluid is known as the capillarity behavior. Is it clear? Okay. Now the rise of liquid surface is also known as capillary rise, while the fall of the liquid surface is known as the capillary depression. Okay. Now it is expressed in the terms of centimeter or mm of liquid. How one can represent the capillarity or capillary behavior? It is represented by the height of water rises in capillary tube or depth of water fall in capillary tube. Okay, and it can be represented in terms of centimeter or mm of liquid. Its value depends upon the specific weight of the liquid, diameter of the tube and surface tension of the liquid. So what are the parameters dependent for the rise of water level? Suppose rise of water level is represented as small as, then it is the function of pause करिए. One minute please. Okay. Okay. Let us restart this slide. There is some technical fault. So the rise or fall of the water level is represented in centimeter or mm of liquid, and the depth of capillary height is dependent on basically the specific weight of the liquid, diameter of the tube and surface tension of the liquid. Okay. Now there is a general expression required to calculate the capillary rise or capillary fall. So this can be represented as the rise of water in capillary H equal to 4 sigma cos theta divided rho GD, and the fall of water in capillary, that is H equal to 4 sigma cos theta divided by rho GD, where sigma is the surface tension, theta is the angle of contact between liquid and glass tube. The value of theta is given for the different types of liquid. For example, if we consider the water and glass, then its angle of contact theta will be equal to 0, whereas in case of mercury and glass tube, the value of contact angle will be 90 degrees. So in the given example, you can easily see how one can calculate the capillary rise or capillary fall. For example, in this problem, calculate the capillary rise in a glass tube of 2.5 mm diameter when immersed vertically in water, and in second case in mercury. Now the take surface tension sigma equal to 0.0725 Newton per meter for water and sigma equal to 0.5 Newton per meter for mercury in contact with air. Now for the the specific gravity for mercury is given as 13.6 and angle of contact, that is theta, is already given 130 degree. So what are the required parameters to be calculated here? Calculate the capillary length. Okay, so let us first write the given data. For example, tube is already given 2.5 mm. When you convert it in SI system, then it will be 2.5 into 10 to the minus 3 meter. Surface tension, that is sigma for water, is given, sigma for mercury is given, and specific gravity of mercury is already given, that is 13.6. Okay, so using the specific gravity of mercury 13.6, you can convert the density, calculate the density of mercury. So it will be equal to the specific gravity of mercury into density of water, and that density of water has a standard value, that is the 1000 kg per meter cube. Okay, let us use the formula, that is the capillary rise for water. So H can be written as 4 sigma divided by rho GD. Okay, and in case of glass and water, angle of contact theta will be 0. So in this equation, all the values have already calculated, that the sigma is given, density of mercury is calculated here, and G has the standard value, diameter of the capillary tube is already calculated. Okay, so if you put all these values, then the value of capillary rise, that is the small length, will be equal to 0.0118 meter or 1.18 centimeter. So this represents the capillary rise. Now in the similar way, you can calculate for the mercury case. For example, 4 sigma cos theta divided by rho GD. So put all the values. 4 sigma cos theta in case of mercury, it is given as the 130 degree, and if you put the required value, that is the density of mercury, is already calculated here, 13.6, G 9.81 into D, that is the 2.5 10 to the minus 3, and this value will be equal to the minus 0.4 centimeter. Minus sign represent the capillary form. Okay. Similarly, this is the general problem based on the simple formula. Using the basic formula, you can calculate the required answer. So for today, I think it is enough, and we will meet for the next class. Thank you. Jai Hind to all.